robustness. And so I wanted to discuss the ResNet architecture and an implementation of it, and how to use a pre-trained model on a different data set, and then evaluate the accuracy of that data set. So let's share the notebook here. So here is my notebook. And this notebook is titled ResNet 18, as seen up here at the top. And what we're going to do is we're going to begin by importing some things like Torch, Torch Vision, NumPy, Matplotlib, GC for garbage collection, and TQDM for a counter. So as always, I try to clean everything out just in case I was working on something. It's always nice to start with a clean workspace. First thing we need to do when loading a neural network or trying to train a neural network is we need something to train on, some data. So what we're going to do is we're going to use the CIFAR10 data set to train a neural network. But what we're going to do is we're going to use a pre-trained neural network, ResNet 18, but we're going to retrain it on a different data set. Now, the means, RGB, for the data set here, and the standard deviation, as seen here, are used to normalize the data set. I can go through how this is computed, but for now, we're just going to say, let's Google it and accept those values. So what we're going to do is we're going to have a batch size of 8 in our train set and a batch size of 1 in our test set. That'll be apparent in another video. But for now, we're just going to have one element in our test set. So we loaded this into a test loader and a train loader, and we want to see what some of the images look like. So what we'll do is we will load up some images and check the labels and see if everything pans out. So here we have a dog, a bird, a plane, another dog, a deer, a truck, a frog, and a car. And if you're interested in the ResNet architecture, I would recommend you go check it out on arXiv. The title of the paper is Deep Residual Learning for Image Recognition. Or you can check out my series of videos that goes over this paper in a little bit more detail. Or you can read it for yourself. Also, instead of having to build out the model architecture, we can load a pre-trained model from PyTorch. So that can be done here. And here are some other models that we can load. But I chose ResNet 18 just to be quick. So we load the model and we look at the fully connected layer just to see what the current status of that is. And so currently the fully connected layer has 512 in features, and out is going to be 1,000 features because there are going to be 1,000 classes from the pre-trained model. The pre-trained model was trained on the ImageNet dataset, which has 1,000 classes. So we want to get rid of that fully connected layer and use a different fully connected layer because CIFAR10 only has 10 classes. So we're going to load in a linear layer with the in features from the previous model, which will be 512, and with the number of classes for CIFAR10, which is 10. And here you can see those classes are plain car, dog, or sorry, plain car, bird, cat, deer, dog, frog, horse, ship, and truck. Great. So we've changed the fully connected layer at the end of the network to have just 10 classes. We're going to retrain the model on our data set, the CFAR 10 data set for 30 epochs. We're going to use a cross entropy loss. Our optimizer is going to be a stochastic gradient descent with a learning rate of 10 to the negative 4 and a momentum of 9.9. So why would we use the CPU if we have a CUDA-enabled GPU? So let's just check to see if we have that GPU. And we can see here that we do have a CUDA-enabled GPU. You can run the NVIDIA SMI command from Bash or from the notebook to get the details of the driver, the temperature, the memory, and some more information here, CUDA version. Great. So what we want to do then is load the model and the loss function to the GPU. Then we're going to iterate over the epochs, and at each epoch we're going to record the loss, the number of images that were correctly classified, and the total number of images in the data set. So we're going to iterate through each batch. The batch will be the input images and the corresponding labels for those input images. We're going to send the input and labels to the GPU, zero out the gradient, zero out the optimizer, pass the inputs through the model to get some outputs. And we're going to compute the loss between the outputs and the labels. We then take a backward step, and then we look to see that if the predictions are correct. And we compute those, add them up, compute the loss, and we iterate through the whole batch. At the end of the batch, we compute the training accuracy, and here I round just so we don't get a bunch of digits. That's just noise. And then we're going to check the test set. So after we go through the training data set, we go through the test set to see how well our model generalizes to input data. So we iterate through the test data set, check the number of correct, compute the accuracy, and then after we've gone through the training loader, the training set, and then the test set, we also log all of that information in a dictionary. We record the epoch, the loss, the training accuracy, and the test accuracy in a dictionary, and then we store that dictionary in a list. And then we do that for 30 epochs. And so you can see here on my local machine, that took about 45 minutes for 30 epochs. And then we have a function here called save model, which takes in the model and a path. And we save the model, torch.save, model.stateDict path. And then we save that to model. So now that we have the model saved, we're going to load up pandas so that we can take the results and easily turn that into a data frame. And so we turn that into a data frame, and then we can look at that data frame and we see that we have epochs as a column, loss as a column, train accuracy as a column, and test accuracy as a column. We can quickly plot the train accuracy and the test accuracy using the internal method plot for a pandas data frame. So we can see here the blue line is the training accuracy, and it increases in a nice smooth fashion. And the test accuracy, unfortunately, kind of flattens out pretty quick. But as you can see, does quite well. We're also able to plot the loss here as a function of epoch. So we can see that the loss decreases almost exponentially as the number of epochs increases. Now, we can quickly check that by doing a semi-log log y equals true, and then recomputing that. So that's a brief overview of how you can take a pre-trained model on the ImageNet dataset and then use that model on a different dataset in order to perform object classification or image recognition. So if you have any questions, let me know down in the comments. Please hit the like button, subscribe for more content, and I will be posting another video after this about how to now attack this model with the fast gradient sine method. Again, my name's Bryce from San Diego State. Have a great day.